Today we're going to talk about errors in hypothesis testing. Once we have our sample data, our evidence, we make a decision either to reject the null hypothesis or fail to reject the null hypothesis. However, we could have made an error in our decision. There are two types of errors in hypothesis testing, type 1 and type 2. Remember, the null hypothesis is a hypothesis of no change, no effect, no difference. Everything is okay. Nothing suspicious. Example that we've used a lot is the company is not cheating. So let's talk about type 1 and type 2 error. A type 1 error is the error of rejecting the null hypothesis when the null hypothesis is true, rejecting when we shouldn't. Type 2 error is the error of failing to reject the null hypothesis when the null hypothesis is false, not rejecting when we should. The probability of a type 1 error is denoted with alpha and is called the level of significance of the test. Thus, a test with alpha equal 0.01 is said to have a level of significance of 1% or to be a level of 0.01 test. The probability of a type 2 error is denoted with beta. Let's look at this example. In this example, a jury decides guilt of an accused based on evidence. So we need to state our null and our alternative hypothesis. Our null hypothesis, accused is not guilty. Our alternative hypothesis, accused is guilty. Okay, so here we're going to use a table to decide the type of error as we go through the consequences, okay? So what we have is when our null hypothesis is true, that means the accused is not guilty or innocent. And when our null hypothesis is false, the accused is guilty. And over here, we have the two things that we could do. This is our decision based on evidence. So this right here, this information is the truth, which is unknown to us. On this side of our table, we're going to have our decision, which is based on the evidence from our hypothesis test. So our two decisions would be reject the null hypothesis or fail to reject the null hypothesis. And when we reject our null hypothesis, the jury finds the person guilty. And when we fail to reject our null hypothesis, the jury finds not guilty. So we have our table set up. Now, when we reject our null hypothesis, jury finds guilty, and the accused is guilty, that's a correct statement. However, when we reject our null hypothesis, meaning we find guilty, and the accused is not guilty, that is a type 1 error. When we fail to reject the null hypothesis, and the accused is not guilty, that would be correct. However, when the null hypothesis is false and we fail to reject the null hypothesis, that's a type 2 error. And this is like a table you can use to organize your thoughts to figure out your type 1 and type 2 error. So let's talk about these. We're still talking about example 1. Jury decides guilt of accused based on evidence. What are the consequences of a type 1 error? So something that could be a consequence of a type 1 error is we have an innocent person who goes to jail. What are the consequences of a type 2 error? A guilty person just walks. They don't go to jail. Which error type has a worse consequence in this instance? A type 1 error, when an innocent person goes to jail. If we were to set alpha in this case, what would we set our alpha to? And we would want to set our alpha to a very small alpha. So small alpha value. What will happen if we set a smaller alpha? We'll make fewer type 1 errors. And that's what we want because that has the worst consequence. But we would make more type 2 errors, meaning more guilty people would go free. However, having an innocent person in jail tends to have a higher consequence. Let's go ahead and look at another example. In 1991, the Environmental Protection Agency adopted the lead and copper rule, which defines drinking water as unsafe if the concentration of lead is 15 parts per billion or greater, or if the concentration of copper is 1.3 parts per million or greater. Suppose a city in the United States is suspected of having unsafe water. The EPA will go in, take water samples, and decide whether or not the city has unsafe water. So our null hypothesis is the water is safe. The alternative hypothesis, water is unsafe. You can use words synonymous with this like fine and bad. That's fine. So here, remember across the top, the truth. This is unknown to us. Okay, so we have when our null hypothesis is true, meaning the water is safe. And when our null hypothesis is false, water is unsafe. Over here, we have our decision based on the evidence. And that's when we reject our null hypothesis, meaning test says the water is unsafe. Or fail to reject our null hypothesis, meaning the test says the water is safe. When we go through, this would be a type 1 error. When our null hypothesis is true, but the test says the water is unsafe. Here would be correct answer when our null hypothesis is false and our test comes back with unsafe water. Here, this would be a correct when the null hypothesis is true, the water is safe, and our test comes back, the water is safe, and this would be a type 2 error. when our null hypothesis is false and the test says the water is safe. So using this information, let's answer the following questions. What are the consequences of a type 1 error? So one of the consequences could be the shutdown of water plants. What are the consequences of a type 2 error? One of the consequences could be health issues. Which error type has worse consequences? So here, a type 2 error would have worse consequences because lives could be in danger. If we were to set alpha in this case, what would we set our alpha to? We would set it fairly high so that the type 2 error has a smaller chance. And what will happen if we set a smaller alpha? If we were set a smaller alpha, the plant gets shut down more often, they might get fined, etc. So now that we've done the two examples, let's look at these questions based on the two examples that we've done. What does set in alpha equal 0.05 or alpha equal 0.01 really tell us? This means that if we use the test procedure many, many times with different samples of the same size from the population. So we would reject the null hypothesis 5 or 1% of the time. So why not always choose alpha equals 0.01, which would require very strong evidence against the null hypothesis? What is the risk? So that would increase the chance of a type 2 error. It would increase our beta. So beta would go up. Can we ever achieve the ideal alpha equals 0 and beta equals 0? No, because the truth is unknown using sample data to discover, quote unquote, the truth. So no, we never can. All we do is we use sample data to discover the quote unquote truth.